which you've missed so far on our last episode, was we were covering Newton's first law. Let's go. All right. Why is it called Newton's first law of inertia? Correct. And what measures said ability? How do you look at two objects and go, that one follows first law better than that one does? Mass. Has more mass. Simply more stuff within it. Absolutely. Why is it weird that it's called Newton's first law of inertia?
Both the constant velocity.
Right. So
Not supposed to slow down.
what's that now?
Not supposed to slow down.
You're right there on the edge. So because it's not going to slow down, two objects with different inertia look exactly the same in first law. Right? A bowling ball and a tennis ball coming at you in space at 3 meters a second. Are you going to be able to look at one or the other and say that one's following Newton's third law better? No, it's weird that first law is called Newton's first law of inertia because you don't actually see inertia in action until you get to second law. Nice transition. All right, so what's second law?
Net force is not zero.
Unbalanced then?
The acceleration is anything but zero.
Correct. It's anything but zero. Basically, if you have an unbalanced force, if it's not one of these, it's unbalanced. Sum of forces is not equal to zero, or it's not in equilibrium, then we know it's going to accelerate. But there's more pieces to that because it's not just that acceleration is not zero. We can calculate exactly how much it is. There's a relationship there. What controls how much? There's two things. What are the two things that control how much acceleration the object has? Force and mass. How does the force affect it? How does force affect it? In other words, I push somebody more. I shove somebody harder, I give them more force, I give them more oomph. What effect should that have on acceleration? More acceleration. It should be direct. Or, actually, let's go back to stuff at the beginning of the year. If I were to graph sum of forces versus acceleration, what shape does it make on the graph? Makes a linear one. Force versus acceleration, or acceleration versus force, would make a linear function, correct? Okay. What would the slope of said function be? Mass. What would the y-intercept be? 0. Very good. You should all be able to do this, but let's humor ourselves one step further. The second thing that Newton's second law says, what's the second thing that contributes to how much acceleration there's going to be? Absolutely, the amount of mass. And if I were to graph acceleration versus mass, real quick, do the work on your page. I'm sure it's super simple. Do that work to show the sketch of what acceleration versus mass looks like. I'm going to give you less than a minute because it should take that quick. Please do it real quick in your notebook. In addition to doing the shape, obviously, we always do the same things. You should know what the constants are. There's probably a direct reason why I want you to think about this. I said acceleration versus mass, but yeah. So the relationship is acceleration versus mass. All right, so real quick rearrangement. What do we have to arrange here? What do we got to do algebraically first? Mass, because we're isolating the y variable a is by itself over n. Very good. And so what shape do you get? Sum of forces, oops, sorry, that was dumb. Acceleration versus mass should give us a hyperbolic function. Now, next question on this particular front is this. What if you wanted to do a linear regression of this? What would what would you have to do in order to do a linear regression so it makes a straight line and you could actually find out what the function is? What's that? What do you mean multiply by? What would I graph instead? In other words, a versus m will always get me a parabola. What do I graph instead, Aslan?
A versus
1 over m will give me what shape? What would the slope of said shape be? It should be the net force on that particular situation. All right. So what we're going to do today is we are going to test that exact law right here. Now we have two options on what. I'm sorry, I skipped third law. Forgive me, real quick. Third law. What's third law? For every force, yeah, for every force, but not action. Every force is an equal and opposite force. And there's some weird stuff when it comes to third law. And I always kind of forget to talk about third law because we focus a lot on the math in the later part of this particular chapter. We do mostly focus on first and second, but third is also kind of important. Oh, shoot, I didn't see that bell ringer. I will have to do that one tomorrow. But there's some interesting things when it comes to first. For example, I've already done this demonstration, but a truck comes by, hits a bug. Which one feels more force? They both feel the exact same amount of force. And there's certain things, people know first, third law, but it's a weird thing. One thing that you can kind of think about, you can wrap your head around, and we'll talk more about later, is this. Third law kind of decides how much you get hit back. For example, if I full-on swung, right, just like gave as hard as I could and punched this wall, I think it's probably fair to say most of you believe I would break my hand, and I would agree with you. However, if I swing just as hard at this piece of paper right here, obviously I did not break my hand whatsoever, which would mean that my hand does not get the same amount of force in that case as it did here, despite the fact I was swinging just as hard, right? I was punching just as hard, but apparently the force in the second case was less. We might think about briefly before we get into that. Why is that? Why on earth would in the second case the force be less in that particular situation? But we'll get back to that a little bit later. All right, I want to talk about today's lab. Today's lab is essentially looking at Newton's second law, and ultimately this should be pretty easy, okay? Because conceptually, Newton's second law should just make sense. The first part of it is push something more, it accelerates more. That should be pretty obvious. Like I've told you, you can try this out with your siblings at home and see whether or not it's true. Okay, shoot, you could try this out in pairs when you go out to the lab and partner up and shove each other back and forth and see, okay, if I shove you more or less, do you accelerate more or less? And we could actually measure how much, which brings me to another situation. We're going to need to be able to measure both of these. Now, mass, that should be pretty easy. What do you have on your table that will be easy to measure mass? Yeah, we have a triple beam balance to get you in grams, but what are we going to need to do in order to measure acceleration? What's that? Sorry, I thought somebody said it. What was it? Say what now? Yeah, but what does this thing actually measure? I think you're pointing to the. This measures time, right? That's all it measures. It's not fancy any more than that. Yes. Yeah, we are. Absolutely, we're going to use kinematics in order to find acceleration. It's almost like kinematics won't go away the entire rest of the year. So what are, now should we probably be dealing in 1D or 2D kinematics here? I would guess 1D kinematics makes the most sense because straight line, and let's make our lives more complicated than others. So that means we got 5 variables in play here. And let's look at probably what the easiest ones are. We need 3 of them in order to calculate the 4th of acceleration, right? So, which variables would probably make sense to set at the beginning? As velocity initial is an easy one. What are we going to do there? 0. Very good. Okay? And next, what else are you going to do? Or either set or measure. Yes? Yeah, let's go ahead and, what are we setting or measuring that? We set the distance. We're literally going to set these apart. Now, a major thing with this is you want bigger numbers because they're going to be more accurate. So let me just tell you that your delta x today should be as large as is convenient. Okay? You want it to be relative. I'm going to let you set it, but we'll just write that down as set. In other words, you decide specifically what it is. Yours doesn't have to be the same as mine, doesn't have to be the same as anybody else's. But I'm going to start to give you the opportunity to change what the variables are. Again, you want it to be bigger, as big as is all right. All right, what else? We're going to measure time, correct. With those 3, then can we calculate acceleration? What equation are we going to use? That same one that comes back time and time again, that's made over say on the first is probably unfortunately, the most useful one that we have. That being said, what nice simplification will happen here to begin with? Yeah, velocity initial in that first term is going to cancel out, so the time is going to cancel out. And solving for A real quick, just humor me real quick, what do? Oh, divide by 1/2. Ooh, let's go ahead and multiply by 2. Okay, multiply by 2 and divide by t squared. And there you go, you got A. All right, now, to show this today, what we've got is a situation very similar to the ramp situation that we had before. But let's go ahead and turn it on. Oh, that's not going to work. Maybe? All right. Apologies. I'm going to have to talk loud here. So this is basically simulating a frictionless surface. Okay? That's why the air is blowing up. Now, we don't need, for the force diagram in this situation, we don't really need to worry about the air as much as just it's ignoring friction, okay? So what we're going to assume here is that the push up is probably what force? Force normal, and obviously the force down is force gravity, right? And you can see first law right here, because if it's balanced, and that is a key assumption today. Anytime, by the way, Spainhour's doing a lab, and he talks about assumptions, you go, oh goody, error analysis, okay? You might write down any sort of assumptions that we say. So the assumption is that this is level, perfectly level. And we're gonna try to do our best on that. I tried to mess with this earlier this morning, but you can also see Newton's first law like this. That until acted on by another force, it should go pretty much at a constant velocity. Now, my opportunities for accelerating this are a multitude. There's a bunch of different ways to specifically accelerate this, right? I could push on it. Obviously, it's not going to work very well right now without the air on, but I could push on it. I could blow on it. But the thing is, we needed a continuous acceleration over a large period of time. So there's two major ways to do this. Both will, in fact, work. One is going to be easier for our purposes today. The first thing that you could do, any ideas, by the way, what could we do to make this accelerate over a large distance? Before I actually just tell you? Yes, Adam. Yeah, what's the problem with just pushing it? Yeah, see, humans don't exactly control their acceleration super carefully. Like, we don't try to put out the same amount of force in the same amount of time. We don't measure it that accurately. And I don't know about you, I can't tell, especially to the Newton, exactly how much I'm pushing. I don't have that, sense, at least in my head. So what would put out a constant amount of force the entire time? Yeah, Matt. Yeah, again, the problem with the external blower situation would be that, like, as it got further away, the force would start to get less. Think about just some simple thing that I could do with this guy right now. Just set up here. I got you. The first thing that we could do, turn it into a ramp. If I turned it into a ramp, what would be nice and give out the same constant amount of force? Gravity, correct. Now, the problem with that is then you got to change the angle, you got to set the angle, and we got to do some weird force diagrams that we haven't gotten into yet. But there's an easier way actually to do it. What you're going to do is we've got this little thing over here that's got stuff for adding to it. One of the things on it has this little guy. It's going to be a flag that sits on top. And that's just there in order to hit the timers right here. But we set a hook on this side, put a string, okay? And then we're going to put a pulley over here on the side. And there is a little mass, so there's a little weight that's in all of yours. You're just going to, there should be 3 different weights on it. Just go ahead and use all of them. Okay. And set it on the side here right now, and by right now I mean assume the blower is not on as it is. What is the force diagram on this guy right here?
Alright, force gravity down, force normal up.
Uh-huh.
And
Matt, go ahead to the next one. Tension to your left and friction to the right. How do we know there's definitely friction right now? Yeah, absolutely. It's not moving. It's not accelerating. We're following Newton's first. What is the force diagram on the hanging mass over here? And how should they relate to each other? You're good. Okay, real quick, I'm going to turn this on.
You said that they were equal.
Right now, yes.
Friction and gravity on the polar.
This is why you want multiple people in your lab. Go ahead quickly, so we can finish this. Go ahead and draw a force diagram of both objects now. It should not be too different, but it will be different. And let's call this the sliding mass and this one the hanging mass. All right. On the hanging mass, what's the force diagram?
Alright, force gravity down,
Force gravity down,
force normal up,
force normal up.
force tension.
Correct. Force tension. So, should it follow the second law? Yes, absolutely. All right, what about the hanging mass?
Wait, why would it be first?
Oh, the force is balanced? Will it accelerate? Oh, and will
yeah.
it accelerate?
Okay.
All right, force diagram on the hanging mass. This is the one that people usually get wrong. What do you got? Force tension up. How will this force tension compare to this force tension? Equal because of? What's that? That's equal because of third law. These are the third order pair. For every force, there is going to be an equal and opposite force. Next, force gravity. Should force gravity be greater, equal, or less than force tension? Should definitely be greater. Why should it be greater? Absolutely. Absolutely. Now, I will tell you that we're going to make an assumption in this particular case. And our assumption is that force tension and force gravity are going to be close to equal here. Now, that's not true. It's 100% not true. If they were equal, this would have to go at constant velocity, which it doesn't. But we're going to make that assumption. To that end, what you're going to see, if they are equal, then force gravity will equal force tension, right?
Yes.
And force tension, obviously, is going to equal force tension, which would mean, in this case, our net force, because these two are going to balance, our net force should be equal. My apologies, people. Our net force is just going to be force of gravity. And how do we calculate the force of gravity? Mass times g. Which mass, though, would this be? Would this be hanging or sliding?
Oh, wait, right.
Hanging, right here. So let's call it NH in this case. All right. So for your lab, what you're going to do, I'm going to try to explain this real quick so we can get you out of there and be doing this as much as possible. You can find the lab, by the way, on Google Classroom right now on exactly what measurements you need to take and everything. But essentially, here's the gist. Okay? You're going to make this particular setup right here. Okay? Now, if I wanted to look, here's my setup. If I wanted to look at a relationship of more force gets more acceleration, what would I change about this setup as I'm trying to do it? Right, I would increase mass hanging and then therefore increase the force of gravity. right? So pull harder, and it should accelerate more. That's honestly the easy one, so we're going to go ahead and do the other one. And that is, we want to look at how inertia affects this acceleration. So what are we going to change? The mass of this, which will control the object's what? Inertia. Correct. So the more inertia it has, what should happen to its acceleration?
Less.
Yes. Last thing I'll cover real quick is this. You guys have done these before, but a just gentle reminder on this. Okay. When you set this up, make sure you put the, it's easier to put the plug kind of in the wall socket right over there. Spread them apart. Make sure it is on pulse today, because you are just getting basically, when you set these, that's controlling your distance right there, however far apart you set them. The other piece of it is this. If this is your first one, it's not in my case, but remember the light turns on when it's broken, and pull just back behind that, right? Because if you start it back here, what do we screwed up? If it starts back here, initial velocity would not be 0 in that case, and that's going to screw up all of your calculations from this particular spot. So you're going to set a distance here, you're going to have this whole setup going on, and then basically you're going to measure this mass right here, this inertia, measure it 4 times. Okay, after you've measured it 4 times, then let's just go ahead and get all of the data today. We're going to do that for a total of 5 different masses up here. The last mass should definitely be above 800. Okay, so I'm going to get out some more masses that you can add to this. There are some masses in here already, but go ahead, even though we might know what these are, always measure it on the scale so you know exactly how much it is. Also, don't forget at the very beginning, measure what your hanging mass is, because it's going to be slightly different for everybody. That should be in your setup as well. When you're done, you should have 4 times for each mass. You should have 5 masses. Okay, you get the average time. You'll calculate the acceleration. We'll have 5 points of data. If we're correct, it should look like this right here. It should look like this right here. You'll have the linear regression. All of these instructions that I'm telling you right now are on the very back of the lab, so you should be able to see that no problem. All right, you work in your groups. There should be a lab table for everybody, including this one up here. Yes?
Do you want us to find the acceleration for each set of times, like for all 5?
No, what you're going to do is you're going to average those times. Make sure, by the way, when you're done with 4 times, that you've actually figured out that they are consistent, right? Check to make sure it's consistent and it makes sense before moving forward. No, you're not going to do accelerations for every time. You're going to get an average time and then get it from there. Okay? All right, off you go.